Hey class, it's Dr. Keller. So what we're going to be doing is we're going to be starting chapter 12 this week. And chapter 12 is looking at the gaseous state of matter. So we're going to be looking at gases. Remember, there's three physical states that exist for most matter. Solid, liquid, and gas. So let's just go back over really quickly what some of the general properties of gases are. Remember that gases have an indefinite shape. So macroscopically, when you look at a gas, or we'll say look through a gas, the particles in the gas do not form a unique shape. They take on whatever the shape of the container is. So if you have a container with round edges, the gas will take on a round shape. If you have a container with rigid, square type edges, then it will take on that shape as well. Also, gases have indefinite volume. This means they not only take on the shape of the container, they take on the full volume of the container. For instance, if I have a cubical container and I put a gas in it, like oxygen, oxygen will not only take up the shape of the container, it will also occupy the entire volume of the container. If I take that same gas, how many particles do I have here? 1, 2, 3, 4, 5, 6, 7. So I'll keep them the same. And I transfer that gas into a long cylinder type of container. It will also take on the shape of the container, and it will take on the volume of that container. So gases have an indefinite shape and an indefinite volume. Whatever the container is, that's its shape and volume. Gases also have very low densities. This means the mass to volume ratio is very small, or there's very little mass inside of a certain volume unit. Basically what that means is remember, density is compactness. So if something is a low density, it's not very compact, or that means that the particles are spread very far apart. So here in this picture, we've shown that these two particles, all the particles have space between them. So there's lots of space between the individual particles. And the last thing we've learned about, toward the beginning of the class, the first chapter, was that the particles of a gas have very high kinetic energies. Kinetic energy is the energy of motion, and that just basically means that these particles are moving all around, and they move in, well, we'll talk about kinetic molecular theory, how they move, but they're moving all around, and when they hit the edge of a container or hit one another, they will just collide and bounce back, and they'll just keep moving. So think about a whole bunch of like random moving particles in here. They're just constantly moving around. Very, very high kinetic energies. So we know the general properties of gases, but it turns out that we can more specifically describe the behavior of a gas or gas particles. And the method used to describe, or the theory that was developed to describe gas behavior, was called the kinetic molecular theory. And what this theory describes, based on 7 assumptions, are what a gas should behave like if it's acting as an ideal gas. So the behaviors that are under ideal conditions for a gas, how those gases behave. So the first part of the kinetic molecular theory is that gases consist of tiny particles. So we know this, molecules or atoms, depending on the gas, is very, very tiny particles. Second, the distance between the particles is large compared to the size of the particles. So here now, this is how we're defining tiny. The particles of a gas are very far apart compared to the size of the particles. So here I've drawn 2 particles, you can barely see them, and they're tiny because the space between them is so large, that's what makes them look tiny. This is why we can see through gases. Like right now, if you look through the air, you're looking through oxygen, nitrogen, and so on, those particles. Well, the reason we don't see the gas is because relative to the space between the particles are so tiny we cannot see them. It's only when they're clumped together in like millions that we start to see the particles in their macroscopic view in the liquid or the solid state. So they're very, very far apart and we can't see them. Third Third postulate of the kinetic molecular theory, gas particles have no attraction for each other. Now, what does that mean? This particle right here, they're not attracted to one another at all. Basically, the particles interact independently to one another. So if this particle's moving and this particle's moving, they don't have an attraction for each other. They act individually, and they are not strayed when they become in close contact. The fourth postulate, the gas particles move in straight lines in all directions, colliding frequently with each other or with the walls of the container. So whenever you have a gas, we're always going to talk about the gas being in a container. I like to use boxes because I can actually draw a box. Okay, so you've got this gas inside of this container here, okay, and I'll make some more molecules. We say that the molecules don't attract one another, and if they don't attract one another, that means they don't bend toward or away from one another as they pass one another, but instead they just are randomly moving in all directions, and they will move in a straight line. The only time that they ever change paths is when they collide against something, either the wall of the container or they bump into themselves. What happens if they collide with each other or with a container? That's the next part of the postulate. The kinetic molecular theory says that the collisions are perfectly elastic. What does that mean? It means when the collision occurs, there's no energy lost. They will bounce back with the same amount of energy that they came in with. The sixth part of the theory says that the average kinetic energy is the same for particles of all gases at the same temperature. The average kinetic energy is the same for all particles of all gases at the same temperature. What in the world does that mean? Well, let's do an example here. Let's say that I have two containers here. I have a container that contains, let's say, helium gas, right there. And I have another container that contains carbon dioxide gas. If I store these containers of gas, same volume of gases, at the same temperature, so let's say they're both at 25 degrees Celsius. Because they're at the same temperature, the particles will individually have the same average kinetic energy. Does that mean these particles are moving at the same speed? Not necessarily. Remember that kinetic energy equals 1/2 mass times velocity squared. 1/2 mv squared. M is the mass, and v is the velocity or rate, how fast the particles move. The kinetic energy is 1/2 the mass times the velocity squared. If you have a higher mass particle, if it has the same kinetic energy as a particle with a lower mass, basically it means that the lower mass particle is moving at a higher velocity, so lower mass, higher velocity, and the higher mass particle is moving at a lower velocity or speed. Think about kinetic energy like two different cars. You've got two different cars traveling down the road with the same kinetic energy. Let's say one of them is a little tiny Volkswagen Beetle. It's a little tiny car. That car has a low mass, so in order to have the equal kinetic energy to say something like a semi-truck, which has a high mass, in order to have equal kinetic energies, the small car has to move at a very high rate. And the large car, the semi-truck, will move at a slower rate. So the rates of the gases is not the same, the rate at which the particles are moving. However, they have the same kinetic energies. That's going to be important later on in the chapter. Let me erase all that. Alright, so all gases at the same temperature, their particles have the same kinetic energy. But if they have different masses, they might be moving at different rates. Alright, let's move on to the last postulate here. The last part of the kinetic molecular theory says that the average kinetic energy is directly proportional to the Kelvin temperature. And notice the Kelvin temperature. That's going to be a main theme in the gas chapter. Whenever we do anything with gases, just always, please, use the Kelvin scale for temperature. But let's read this again. It says the average kinetic energy is directly proportional to the Kelvin temperature. I'm going to write that an equation mode or a proportionality mode. If you have the kinetic energy of a gas proportional to the temperature in Kelvin, what does that mean? Proportional means they move in the same direction. So if I increase the temperature of the gas, I increase the kinetic energy by the same proportional quantity. If I decrease the temperature of the gas, I decrease its kinetic energy, which means if it has the same mass, then basically means it's moving at a slower rate. So particles that are at higher temperatures, gases at higher temperatures move at faster speeds, and gases at lower temperatures move at lower speeds. Now I'll give you an example of this. Have you ever microwaved popcorn before? Because I know I have. When I was about 7 years old, my mom let me microwave some popcorn. And so I did, and then the popcorn timer was up, the popcorn was ready to come out. And one of the warnings on the bag says, be careful, the bag's hot, do not open immediately. You're always supposed to let it cool down first. Because of the steam, the water molecules are in the gaseous phase, and they're very, very hot. So one time, when I was 7, I decided I was going to open up as soon as that popcorn stopped popping. I opened up the popcorn bag, and I loved the smell of the butter because it was yummy. And so I opened it up, and guess what? The steam came out of the bag right in my face. And it hurt so badly, like as I was sniffing in, oh, my nose, it hurt. I know this is silly, but I was 7, so what was happening? Well, what was happening was, remember when popcorn pops, the water is released, and now that steam, that water in the gaseous phase, was very, very hot. Because it was very hot, the particles moving at a very, very, very high speed. So the fact that the steam hurt me is because those steam particles were literally punching me in the face, right, as they were coming out. Now, if I take, let's say, a bath or something, or turn on the shower, that's at a much lower temperature than something coming out of the microwave. So the water coming off of there may be warm, but those particles at a lower temperature, so they're moving at a lower kinetic energy, they don't actually hurt us. And so that's kind of what that means. If you have a gas at a higher temperature, the kinetic energy on average of the particles will be higher. If you have a lower temperature, the kinetic energy will be lower. So these are the postulates that define an ideal gas. Basically, what does that mean? If you have a gas and you monitor its behavior, and it meets all of these different conditions then of the kinetic molecular theory, then you have what we call an ideal gas. Okay? So if all of these conditions are met, that means that you basically have a gas. It's acting like a gas, it's a gas. Sometimes, though, gases deviate from ideal behavior, which means they stop acting completely like a gas, or like these conditions state, and they start behaving what we call like a real gas. So let's talk about what a real gas is. Alright, so when are the conditions when gases do not behave ideally or as they are in the kinetic molecular theory? Well, I will first say that if you have a real gas, like, oh, here's some oxygen, here's some nitrogen, most of the time they'll behave like an ideal gas under ordinary temperature and pressure conditions. And we'll talk about what that means, but standard temperatures, standard pressures. However, if you start to deviate away from standard temperatures and standard pressures, your gases will not behave ideally. The first condition where gases start to behave ideally, or unideally, is if you have high pressures. If you have high pressure. Now what's happening here? If the pressure is too high, let's just go ahead. Actually, let me make a different example. Let's say we have a balloon, because I think we all have experience with a balloon before. And let's say it's a balloon that's made out of indestructible material, though. So we can actually change the volume. And let me actually go even further. Maybe a piston. A lot of you are familiar with cars and the pistons, where the piston head goes up and down. So the piston head here can go up or down the shaft. As this slides frictionless, it can go down, it can go back up. Okay, so let's say that you have a gas and the piston's completely open. You're at a high volume. When you're at a high volume, you've got lots of space for the gas to occupy. That gas, the particles between it, are relatively far apart. And we said when the gas particles are relatively far apart, part of the kinetic molecular theory, you have an ideal gas. But if this piston here gets compressed down, you can actually change the volume of the container. And if you press it down enough, you can actually force those particles to become very, very tight and close to one another, as opposed to very far apart. When the particles get too close to one another, does that look like a gas anymore? No, the particles start to touch and they cannot get away from each other. The distance between particles is smaller and the particle size feels larger. So the particles start to feel one another. They're slipping and sliding instead of bumping against one another. We're almost in the liquid state. Doesn't that look more like a liquid that I've drawn there than a gas? You can't see through it as much anymore, can you? Now maybe it's still a gas, but it's becoming more liquid-like. So this is an instance when the gas stops behaving ideally at very high pressures. When's another example of when gases behave unideally? The second example is when you're at low temperatures. When you're at low temperatures, what happens? Well, in the kinetic molecular theory, we said that the kinetic energy is proportional to temperature. Okay, so if you go down to really low temperatures for a gas, remember gases, you have solid, liquid, gas. When you get near the condensation point, or the point at which the gas becomes a liquid, when you get more near that temperature, the kinetic energies of the gases become much lower. Now, why is that important? Remember how we described gases? We said gases typically have high kinetic energies. When the particles begin to slow down, as they're moving past one another, they start to behave unideally because the gas particles, as they move past one another, the collisions become inelastic. They start to feel one another's presence, the protons and electrons, those attractions. So they don't act completely independent of one another anymore. And their kinetic energies just aren't high. So once again, if you have lower kinetic energies, are you really behaving like a gas? No, you're starting to behave more like a gas that's almost a liquid. Both of these conditions, by the way, high pressure and low temperature, are both conditions used by chemists to condense gases. Condense means to go from the gaseous phase to the liquid phase. So both of these conditions are used to convert gases into the liquid phase. So it makes sense that the particles are not behaving ideally like gases. So this is what a real gas behavior is versus an ideal gas behavior. Alright, so now let's talk about how gases move. There's two different ways that gases can move around. If you have a container and you open up the container to a new container, there's two different processes that it can occur. So the first thing we're going to talk about is the process of diffusion. Diffusion. You've probably heard of this before. A lot of people have biology backgrounds and they've heard these terms before. What does diffusion mean? Diffusion means the ability of two or more gases to mix spontaneously until they form a uniform mixture. Okay? So diffusion is basically the mixing of gases until they form a uniform mixture. What do I mean by this? Well, let's change your colors here. Let's say I have two different gases and two different round bottom flasks. They're closed containers and they're separated from one another by a stopcock. This is the stopcock that I've drawn here in the middle. So the stopcock is the barrier preventing these two flasks from mixing. So let's say I have one type of gas in one container, and in the other container I have a different gas. Right? Now, the two gases are in different containers that hold apart. When I open the stopcock, that is, when I open it up over here to where there's no barrier between the containers, what happens on this side? Well, what happens is it takes time for the two gases to mix or to diffuse until you have a homogeneous mixture or a uniform mixture throughout the entire container. When the stopcock is first opened, when I first open the stopcock here, okay, let's see here. It's hard to go back and forth drawing. Okay, so when I first open that stopcock, immediately we don't have a homogeneous mixture or a uniform mixture of the two gases seen throughout. We know it takes time because according to the kinetic molecular theory, the particles are moving randomly, independently in all directions. So the particles will randomly start colliding with one another and maybe moving across this way. One red one might make it into the other container and begin to bounce around. One of the blue ones over here might move over and randomly kind of come over here until it reaches the container. So it takes time for gases to diffuse. When they finally diffuse completely, when diffusion process is complete, how will you know diffusion is complete? The mixture is uniform throughout, meaning the concentration at any point in the new vessel will be the same for the mixture of gases at every point. So over here, when diffusion process is done, we have a homogeneous mixture of gases. All right, so that's the process of diffusion, mixing the gases. What is the other way that gases can move? Instead of randomly combining, they can actually move in one direction specifically. This is the process of effusion. Effusion. Effusion is a term that means the escaping of a gas. Oops, the escaping of a gas. I don't want to write gases. So what do I mean by escaping? Well, the technical definition of effusion is when gas molecules pass through a very small hole from a container that's at a high pressure to one that's at a lower pressure. What in the world do I mean by that? Well, let's take this tire for an example. This is a very quick tire I drew. But let's say that inside the tire there's gas particles, and they're at a high pressure, so I'm going to draw them close together. Tires typically are at a high enough pressure that they hold your car up, right? So the PSI is usually written on the outside of the tire. So there's all these particles in there. They're jostling around. They're bouncing and colliding with one another in the sides of the walls, which is what's keeping your tire inflated, right? The particles are at very high energies. They're pushing with lots of pressure against the sidewall of your tire. You don't want your tire to have a hole in it, because what happens is when a hole gets in the tire, like on the right, the particles begin to escape very rapidly through that hole. Notice the particles are not kind of randomly moving. They're moving in one specific direction out the hole. Now, also remember that if you're in an environment where you have a tire, there's a gas on the inside of your tire. It might be nitrogen you put in there. And then on the outside of the tire, you've got your atmospheric gases, right? So I'm going to draw my atmospheric gases out here. Now, the question is, when I slice a hole in that tire, do you have to worry about your tire exploding because these gases are going to enter the tire? And the tire getting so full and such high pressure that the tire is going to explode? No, you don't worry about that, right? Instead of the gases on the outside and the inside diffusing or mixing equally or entering, it always turns out that the gas at the higher pressure will escape from the hole to get to the lower pressure. So we know our tires have a very high pressure on the inside. So here we have a high pressure. And outside in the atmosphere we have a lower pressure. The higher pressure gases will always escape to the lower pressure until the pressure difference is equal. So does the tire escape forever? No. It could go flat, but whenever the pressure inside of the tire is equal to the pressure on the outside of the tire, the effusion process, so the escaping of the gas, stops. At that point, there's a hole in your tire. There's particles on the outside of the atmosphere. There's particles on the inside. Now you will begin a diffusion process where gases can come in and out. But when the pressures are unequal, you have effusion of a gas. So when it comes to the process of effusion, do all gases, like if I had oxygen versus carbon dioxide versus helium versus neon versus nitrogen, if I have a tire that's equally filled at the same pressure for each of those, and I slice a hole into all of the tires at the same time, Well, they all fuse at the same rate, and all of the tires become flat at the same exact second, at the same rate. The answer is no. Different gases fuse at different rates. If I have a gas that's a lighter weight gas, meaning its molar mass is low, it will actually fuse at a very fast rate. Those particles will be moving quickly. And if I have a gas that weighs a lot, like argon, that weighs a lot more than helium, the argon gas is heavier, and because if you're at the same temperature, the average kinetic energies are the same. Because it's a higher mass, it'll move or fuse at a slower rate out of the tire. So if I filled 2 tires, one with helium, which is a lightweight gas, and one with argon, which is a heavyweight gas, the helium tire would become flat faster than the argon tire. Much faster. How much faster, you might ask, though? You could do a competition. How much faster does argon diffuse from a container than helium does? I had to remember which one I talked about. So how much faster does argon fuse versus helium? We can actually calculate how much quicker one gas will fuse from another using an equation called Graham's law of diffusion. Graham's law states that the rate of diffusion of a gas is inversely proportional to its mass. So the rate, that's how fast something occurs, the rate of diffusion of a gas is inversely proportional to its molar mass. So the higher your mass, the slower the rate. The lower your mass, the higher your rate of diffusion. And we can compare two gases' rates. If I know the rate of gas A, and I want to compare it to the rate of another gas B, rate A versus rate B, if I want to do a comparison of rates of diffusion, I can calculate 2 different gases' rate of diffusion ratio based on the inverse of their molar masses, or the square root of the inverse of their molar masses. So I'm going to take this square root, and if I have gas A on top, I'm going to put the molar mass of gas B on top. And if I have gas B on bottom, I'm going to put the molar mass of A on bottom here. So this is Graham's law of diffusion equation. Notice there's a square root in it. Make sure you see that square root. The rate comparison between gas A and B is equal to the square root of the inverse of the molar masses of the gases. So what does that mean? Let's do an example and just use the equation. It says in this problem over here on the right, it says how much faster will hydrogen diffuse than methane? Alright, let's look at this equation. And we want to compare hydrogen with methane gas. So I'm going to come in here and I'm going to actually change A and B to real compounds. So we've got the rate of hydrogen, and I want to compare the rate of hydrogen with the rate of methane. So these are our 2 gases. So basically what I want to do is I want to compare the square of the root of the inverse of their molar masses. So instead of molar mass of B and molar mass of A, let's put the gases in here. In order to calculate the rate difference, so the rate proportionality ratio, I take the molar mass of methane compared to the molar mass of hydrogen. Okay, so now I need numbers. I'm actually going to get numbers out of this. So I'm going to take the square root. What's the molar mass of methane? Well, methane is CH4. Carbon weighs 12 and hydrogen weighs 1 apiece. So it's basically 16 grams per mole. And I'm just doing this as an example. I'm not going to get the decimals out here. So we have the square root of 16 grams per mole for methane divided by the square root of, or divided by the molar mass of hydrogen. Hydrogen is H2, so hydrogen weighs 1 times 2. 2 grams per mole is the molar mass of hydrogen. You should be pretty good at that by now from the last test. So I've got the grams per mole of each. I'm taking the square root. So basically, when I solve, it's going to be the square root of 16 over 2, which is the square root of 8. Well, what's the square root of 8? If you get out your calculator, which you should always get out your calculator instead of just trusting me. because you'll have to do this eventually, right? So what's the square root of 8? The square root of 8 is about 2.8. Now there's no units because the grams per mole cancels out. So what does the 2.8 mean? Well, the rate that hydrogen effuses versus methane is 2.8 times faster. The question was, how much faster will hydrogen effuse than ethane? 2.8 times faster. That's what that means. All right. Now, that's using the calculation. That's using the actual equation for Graham's law. You can also use Graham's law of effusion just to make general observations about gases. So you could get down to the actual rate comparison of the gases using their molar masses, or you could just use the fact that the kinetic energy, or the rate that a gas effuses, is inversely proportional to its molar mass. Now, what does that mean? If you have a high weighing gas, a high molar mass, you're going to have a low rate. I always thought about this, and I've heard this, I didn't make this up, but one time one of my chemistry professors told me, skinny kids run faster, which means that if you're lightweight, you're going to have a lot of energy, just like the kid that's heavier, maybe a lot larger, maybe he's more muscular. But the lightweight kid can run so much faster, it can carry its mass so much quicker than the heavier kid. So skinny kids run faster. One of my chemistry professors told me that, and it's always stuck with me. That's Graham's law. The rate that a gas effuses is inversely proportional to its molar mass. So here's another question here. It says, which gas will effuse, it should say effuse, most rapidly? The gas that weighs less will move the fastest. So here we've got helium, neon, argon, and krypton. Hey, that looks a lot like my noble gas column there. Helium is the lightest weight of the gases, so it will effuse the most rapidly. By the way, krypton is the heaviest of the gases here, so it will be the one that effuses the slowest.